Hi everybody, this is our third lecture on this very lesson, electric charges and electric fields. So let me write the name of lesson. Electric charges and fields, third lecture. And today's topic is Coulomb's law. French scientist Charles Augustin Coulomb in 1785 only, and he measured the force between two charged particles very accurately. And what the best part was that he was not knowing even the magnitude of charges on the 2 point charges. So uh, he he formulated one law also regarding the force acting between the two charged particles. So if the two if the 2 point charges which are at rest are kept at some distance, then according to Coulomb's law, the force F acting on the point charges say Q1 and Q2, which are kept at a distance r, is proportional to product of charges Q1 Q2, and it is inversely proportional to square of the distance between the two charges. So when you combine the two things, you get F is proportional to Q1 Q2 divided by R square. Now it implies that F is equal to small k Q1 Q2 by R square. So we get a formula here regarding the electric forces between 2 point charges kept at rest at some distance from each other. Now small k is equal to 1 by 4 pi epsilon naught. Here k is a proportionality constant. Called electrostatic force constant. Small k. Do remember. And it is equal to small k, it is equal to 1 by 4 pi epsilon naught. Here a new term is coined. Here it is called epsilon naught. epsilon naught. Epsilon naught is permittivity of free space. Free permittivity of free space. Now its value is equal to 9 into, nearly it is equal to 9 into 10 power 9. Okay, and its unit you can take from here. Electrostatic force constant K has unit. From here we can find the unit of electrostatic force constant. It is equal to Newton meter square divided by Q1 Q2. For Q1 Q2 you can take Coulomb square. So its unit is Newton meter square. Newton meter square divided by Coulomb square. Now what is permittivity? When you place some charge in a medium, in any surrounding, and it has to apply some force on some other charge which is at some distance, so the medium should permit the charge to apply some force by creating some field. So all the medium does not allow the charge to apply force equally, and the extent up to which any medium allows any charge to apply force by creating electric field lines, this extent is called permittivity. Permittivity is the extent to which any medium allows the electric field lines to pass through it. So electric force is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square. And yes, it is a scalar form. I will be explaining its vector form also. So first of all, let me clear all the details in the scalar way. This is force electric when this is force electric when the two charged particles are kept in vacuum at some distance r. Now if the same two charges are kept at the same distance, r in one medium other than vacuum. then the force as per Coulomb's law is force in medium is equal to 1 by 4 pi epsilon q1 q2 by r square. Let this be equation B. Now on dividing A by B, force in vacuum divided by force in medium is equal to 1 by 4 pi epsilon naught divided by 1 by 4 pi epsilon q1 q2 by r square divided by q1 q2 by r square. So this term, you can say that this term can be cancelled from the numerator and denominator. Here this term also will be cancelled and it becomes equal to epsilon by epsilon naught. So it implies that force in vacuum divided by force in medium is equal to ratio of epsilon, permittivity of medium to permittivity of free space, and this is termed as relative permittivity. Here epsilon r is equal to relative permittivity. And the same ratio is also called dielectric constant, and this constant is capital K. Just do remind, there are two K's in this Coulomb's law. So the force constant, dielectric force constant, is small k, and relative dielectric constant is capital K. Electrostatic force constant is small k and dielectric constant is capital K. This capital K is called dielectric constant, and this is also called specific inductive capacity. Okay. Now while doing numericals, you have to keep these things in mind, because always you have been given different terms. Like suppose you have been given relative permittivity. You have been given relative permittivity. So you find permittivity in terms of relative permittivity and absolute permittivity. So your equation B becomes equal to, so equation B becomes force in medium is equal to 1 by 4 pi epsilon naught epsilon r q1 q2 by r square. This complete term has value 9 into 10 power 9. Nearly it is equal to this one, this value. And this is divided by epsilon r. q1 q2 by r square. And relative permittivity of water is 80. Dielectric constant of water is equal to 80. So sometimes we will be given permittivity. In some questions will be given permittivity, but in some questions will be given, instead of, in place of permittivity, you will be given relative permittivity. Then also you have to do in this way. In some question you will have to given dielectric constant K. So the same formula but different terms will be given in numericals. Now force in medium water. In water, dielectric constant K is equal to 80. It means that when you place dielectric constant in this formula, and if it is 80, so denominator becomes 80 and force in that medium, water medium, becomes 1 by 80 times the same force when the same two charges are placed in vacuum at the same distance. So force is reduced 80 times. 1 by 80 times the force in vacuum. So these are the terms you must remember. Firstly, I have used permittivity of free space, and it has some unit. Its unit is equal to, here you have force and at the same direction you have Q1 Q2 divided by R square. So from here you can get unit of permittivity as Newton meter square divided by Coulomb square. But the relative permittivity, epsilon R is ratio of two permittivities. It is permittivity of any medium, divided by permittivity of free space. So it is ratio of same thing, so it is unitless. If you write the unit, Newton meter square per Coulomb square divided by Newton meter square divided by Coulomb square. So unit is cancelled. So it is a unitless quantity. Dielectric force constant. Dielectric constant. It is also unitless. If you put in formula, so you will find that dielectric constant K is also unitless. So this is the scalar form of force. In scalar form you can write F is equal to small k divided by capital K Q1 Q2 divided by R square. Scalar form of Coulomb's law. Now, since force is a vector quantity, so a scalar form will not do. So let us find its vector form too. Vector form of Coulomb's law. Suppose we have two charges, point charges Q1 and Q2, placed at some distance R. So if if the product of charges is greater than 0, it means either both are positive or both are negative, because two negative quantity on multiplying becomes positive and a quantity greater than 0. So it means either both are positive or both are negative, then only Q1 into Q2 is greater than 0. Now we know that like charges repel each other. We know that like charges repel each other. So let us draw the direction of forces on the two charges. Let me draw once again, Q1, Q2. These are two like charges. Either they will be positive or they will be negative, because Q1, Q2 is greater than 0. So, being like charges, the repulsive force, a force with direction opposite to each other will be there. Suppose this charge on Q1 is called F1 due to 2. This charge is called F1 2. And another charge, another force on Q2 is called Q2, and this is due to 1, F21. So there are two forces, and the two forces are in opposite direction. Now let the position vector or let me tell it, displacement vector of Q1 from Q2 is R21. This is displacement vector. Here R21 is displacement vector of Q2 from Q1. Okay. Now let us write equation of force on any one charge. So let us write force on Q1. So force on Q1 is given by F12. I have taken F12. Okay. And this is equal to, firstly we will write magnitude. So this will be equal to small k Q1 Q2 by R square, and then this is magnitude, and beside of this we will write direction. So tell me, what is the direction of force? This is just opposite to R21 vector. This is just opposite to. So I will write in negative with it a negative sign, minus R21, unit vector of R21. Okay, so R21 cap. Here R21 cap is unit vector in a direction from Q1 to Q2. Here R21 cap is unit vector in a direction from Q1 to Q2. Why I have written negative sign? Because the force on Q1, you can see in diagram, force on Q1 is just opposite to this displacement vector. R21 is along Q2 and F12 is just opposite Q2. So I have taken a negative sign. Now let us take it as equation 1 and let us find force on Q2. It is given by, here one more thing, this displacement, magnitude of displacement, this is the magnitude of displacement and square of this. So magnitude can be either R21, magnitude of R21, or it can be magnitude of R12 also. So anything we can write. Here I am writing R21 as it is already I have used here R21. So I am writing here R21. Now let us come to this case. Let us find force on Q2, and this I have written as F21. This force is equal to, firstly we will be writing magnitude of it, K Q1 Q2 by R21 modulus magnitude square into this direction. Let us find in which direction this force is acting, and this is in the same direction of the direction of displacement vector R21. So you can write plus R21 cap. Let this equation be 2. If we compare equation 1 and 2, we find that on comparing equation 1 and 2, we find that F21 is equal to minus of F12. So the electric forces are equal and opposite in nature, and it means that they make pair production is there. There are two forces which are equal and opposite. So the forces are equal and opposite. The forces do pair production. Okay. So this is the vector form. And which vector form? This is unit vector form. This is your, so this is your unit vector form. Firstly scalar form. Scalar form, force is equal to K Q1 Q2 divided by R square, and this is unit vector form. Let me write it. F12 is equal to K Q1 Q2 by, you see, R21 minus R21 modulus of R21 square and R21 unit vector form. But if Let us suppose, let the two charges are of opposite nature. Then Q1 into Q2 is smaller than 0. Now let us learn this by making some diagram, because diagram 2 is very important for this kind of charges. You have to draw diagrams in your examination. So let me do also that. Let there be two charges Q1 and Q2, and both are of opposite nature. So obviously, unlike charges attract each other, the forces will be of this kind. You can show the forces by arrow along the same direction. Now if F1, 2 is the force acting on Q1 and F2, 1 is force acting on Q2, and the displacement vector is R2, 1 vector, then again let us write the forces on the charges. Now force on force on Q1 F1, 2 is equal to, firstly we will write magnitude of force K Q1 Q2 divided by R21, magnitude of this vector square. This is your magnitude, and then we will write direction. And you can see that this force is in the same direction in which the displacement vector R21 is. So we can write R21 cap. This is unit vector. Here R21 cap is unit vector from Q1 to Q2. Similarly, F21 vector is equal to K Q1 Q2 divided by modulus of R21 vector square of that. And from here, this diagram, you can say that force vector direction and R21 vector direction are opposite. So while writing the direction of unit vector of force F21, we'll have to put a negative sign here, minus R21 cap. So when we again compare equation 3 and 4 on comparing 3 and 4, again we get the same result, that is F21 is equal to minus of F1. So forces are produced in pairs. So electric forces, rather I should say electric forces. Electric forces are produced in pairs. So we have two forms, scalar form, unit vector form. Now position vector form. Third one is position vector form. as we know that unit vector R12 unit vector is equal to position vector divided by modulus of position vector, magnitude of position vector. This gives unit vector. Therefore, and R21 unit vector is equal to position vector R21 divided by modulus of R21. We can use these two results, these two formula in this formula of force. So from here, this equation is where is, yeah. So from here even F12 vector is equal to, it is given F12 is equal to K Q1 Q2 K, so from 3 F12 is equal to K Q1 Q2 divided by R21 vector modulus of it square into, it is given, yes, from 3, what is this? Yes, R21 cap, and this is equal to, this force on 1 due to 2 is equal to K Q1 Q2 divided by R21 vector modulus of R21 vector square into, and we put the value of R21 cap, unit vector R21 cap, and this is equal to R21 vector divided by modulus of R21. Okay. So formula of force becomes equal to small k Q1 Q2 divided by R21 vector modulus of it, and this becomes 3 square here and multiplied by 1 more, so their power becomes 3, and the vector is displacement vector R21 vector. So this is another form of force, and this is displacement vector force. In the form of displacement vector. This is in the form of displacement. Now next, so the same force can be written, formula of the same force can be written in 4 ways. First one is scalar form, second one is unit vector form, third one is displacement vector form, and now fourth one is position vector form. Position vector form. Let me do some vector here, vector calculation here. Suppose we have two particles Q1, Q2 point charging, and its distance, directed distance from origin of the two charges are R1 vector and R2 vector respectively, and the displacement vector from Q1 Q2 Q2 is R21 vector. So from triangle law of vector addition, let me put the direction of these vectors too. So from triangle law of vector addition, R21 vector plus R1 vector is equal to R2 vector. Therefore, R21 vector is equal to R2 vector minus R1 vector. Now let us put this value in equation. Let me give its name. This is 5. So in equation 5, F12 is equal to vector F12 is equal to K Q1 Q2 by R21 vector modulus of R21 vector whole cube into displacement vector R. Yes, this one. Now let us put the value of displacement vector in terms of position vector. So we find that F12 vector is equal to K Q1 Q2 and R2 minus R1 modulus, no, not modulus,